Thermodynamics is about transfers of matter and energy that can actually occur between bodies of matter and radiation. Each participating body is initially in its own state of internal thermodynamic equilibrium. The bodies are initially separated from one another by walls that obstruct the passage of matter and energy between them. The transfers are initiated by a thermodynamic operation. Some external agency makes one or more of the walls less obstructive. This establishes new equilibrium states in the bodies. The second law of thermodynamics then states that the sum of the entropies of the participating bodies always increases. In an idealized limiting case, that of a reversible process, this sum remains unchanged. The transfers invariably bring about spread, dispersal, or dissipation of matter or energy, or both, amongst the bodies. They occur because more kinds of transfer through the walls have become possible. If, instead of making the walls less obstructive, the thermodynamic operation makes them more obstructive, there is no effect on an established thermodynamic equilibrium. The second law describes irreversibility in thermodynamic processes that actually occur. It is a consequence of the asymmetric character of thermodynamic operations, and not of any internally irreversible microscopic properties of the bodies. Thermodynamic operations are macroscopic external interventions imposed on the participating bodies, not derived from their internal properties. Of course, thermodynamics relies on presuppositions, for example the existence of perfect thermodynamic equilibrium, that are not exactly fulfilled by nature. The second law is an empirical finding that has been accepted as an axiom of thermodynamic theory. Statistical thermodynamics, classical or quantum, explains the microscopic origin of the law. The second law has been expressed in many ways. Its first formulation is credited to the French scientist Sadi Carnot in 1824. Introduction. Intuitive meaning of the law. The second law is about thermodynamic systems or bodies of matter and radiation, initially each in its own state of internal thermodynamic equilibrium, and separated from one another by walls that partly or wholly allow or prevent the passage of matter and energy between them. The law envisages that the walls are changed by some external agency, making them less restrictive or constraining and more permeable in various ways. Thereby a process is defined, establishing new equilibrium states. The process invariably spreads, disperses and dissipates matter or energy, or both, amongst the bodies. This is quantitatively described by increase of entropy. It is the consequence of decrease of constraint by a wall. An increase of constraint by a wall has no effect on an established thermodynamic equilibrium. For an example of the spreading of matter, one may consider a gas initially confined by an impermeable wall to one of two compartments of an isolated system. The wall is then removed. The gas spreads throughout both compartments. The sum of the entropies of the two compartments increases. Reinsertion of the impermeable wall does not change the spread of the gas between the compartments. For an example of the spreading of energy, one may consider a wall impermeable to matter and energy initially separating two otherwise isolated bodies at different temperatures. A thermodynamic operation makes the wall become permeable only to heat, which then passes from the hotter to the colder body, until their temperatures become equal. The sum of the entropies of the two bodies increases. Restoration of the complete impermeability of the wall does not change the equality of the temperatures. The spreading is a change from heterogeneity towards homogeneity. It is the unconstraining of the initial equilibrium that causes the increase of entropy and the change towards homogeneity. The following reasoning offers intuitive understanding of this fact. One may imagine that the freshly unconstrained system, still relatively heterogeneous, immediately after the intervention that increased the wall permeability, in its transient condition, arose by spontaneous evolution from an unconstrained previous transient condition of the system. One can then ask, what is the probable such imagined previous condition? The answer is that, overwhelmingly probably, It is just the very same kind of homogeneous condition as that to which the relatively heterogeneous condition will overwhelmingly probably evolve. Obviously, this is possible only in the imagined absence of the constraint that was actually present until its removal. In this light, the reversibility of the dynamics of the evolution of the unconstrained system is evident. In accord with the ordinary laws of microscopic dynamics, it is the removal of the constraint that is effective in causing the change towards homogeneity, not some imagined or apparent irreversibility of the laws of spontaneous evolution. This reasoning is of intuitive interest, but is essentially about microstates, and therefore does not belong to macroscopic equilibrium thermodynamics, which studiously ignores consideration of microstates and non-equilibrium considerations of this kind. It does, however, forestall futile puzzling about some famous proposed paradoxes, imagining a derivation of an arrow of time from the second law, and meaningless speculation about an imagined low-entropy state of the early universe. Though it is more or less intuitive to imagine spreading, such loose intuition is, for many thermodynamic processes, too vague or imprecise to be usefully quantitatively informative, because competing possibilities of spreading can coexist. For example, due to an increase of some constraint combined with decrease of another. The second law justifies the concept of entropy, which makes the notion of spreading suitably precise, allowing quantitative predictions of just how spreading will occur in particular circumstances. It is characteristic of the physical quantity entropy that it refers to states of thermodynamic equilibrium. General significance of the law. The first law of thermodynamics provides the basic definition of thermodynamic energy, also called internal energy, associated with all thermodynamic systems, but unknown in classical mechanics, and states the rule of conservation of energy in nature. The concept of energy in the first law does not, however, account for the observation that natural processes have a preferred direction of progress. The first law is symmetrical with respect to the initial and final states of an evolving system, but the second law asserts that a natural process runs only in one sense, and is not reversible. For example, heat always flows spontaneously from hotter to colder bodies, and never the reverse, unless external work is performed on the system. The key concept for the explanation of this phenomenon through the second law of thermodynamics is the definition of a new physical quantity, the entropy. For mathematical analysis of processes, entropy is introduced as follows. In a fictive reversible process, an infinitesimal increment in the entropy of a system results from an infinitesimal transfer of heat to a closed system divided by the common temperature of the system and the surroundings which supply the heat. The zeroth law of thermodynamics in its usual short statement allows recognition that two bodies in a relation of thermal equilibrium have the same temperature, especially that a test body has the same temperature as a reference thermometric body. For a body in thermal equilibrium with another, there are indefinitely many empirical temperature scales, in general respectively depending on the properties of a particular reference thermometric body. The second law allows a distinguished temperature scale, which defines an absolute thermodynamic temperature, independent of the properties of any particular reference thermometric body. Various statements of the law. The second law of thermodynamics may be expressed in many specific ways, the most prominent classical statements being the statement by Rudolf Clausius, the statement by Lord Kelvin, and the statement in axiomatic thermodynamics by Konstantin Carathéodory. These statements cast the law in general physical terms, citing the impossibility of certain processes. The Clausius and the Kelvin statements have been shown to be equivalent. Carnot's principle. The historical origin of the second law of thermodynamics was in Carnot's principle. It refers to a cycle of a Carnot engine, fictively operated in the limiting mode of extreme slowness known as quasi-static. so that the heat and work transfers are between subsystems that are always in their own internal states of thermodynamic equilibrium. The Carnot engine is an idealized device of special interest to engineers who are concerned with the efficiency of heat engines. Carnot's principle was recognized by Carnot at a time when the caloric theory of heat was seriously considered, before the recognition of the first law of thermodynamics, and before the mathematical expression of the concept of entropy. Interpreted in the light of the first law, it is physically equivalent to the second law of thermodynamics, and remains valid today. It states the efficiency of a quasi-static or reversible Carnot cycle depends only on the temperatures of the two heat reservoirs, and is the same, whatever the working substance. A Carnot engine operated in this way is the most efficient possible heat engine using those two temperatures. Clause's statement. The German scientist Rudolf Clausius laid the foundation for the second law of thermodynamics in 1850 by examining the relation between heat transfer and work. His formulation of the second law, which was published in German in 1854, is known as the Clausius statement. Heat can never pass from a colder to a warmer body without some other change, connected therewith, occurring at the same time. The statement by Clausius uses the concept of passage of heat. As is usual in thermodynamic discussions, this means net transfer of energy as heat. It does not refer to contributory transfers one way and the other. Heat cannot spontaneously flow from cold regions to hot regions without external work being performed on the system, which is evident from ordinary experience of refrigeration. For example, in a refrigerator, heat flows from cold to hot, but only when forced by an external agent, the refrigeration system. Kelvin's statement. Lord Kelvin expressed the second law as it is impossible, by means of inanimate material agency, to derive mechanical effect from any portion of matter by cooling it below the temperature of the coldest of the surrounding objects. Equivalence of the Clausius and the Kelvin statement. Suppose there is an engine violating the Kelvin statement, i.e., one that drains heat and converts it completely into work in a cyclic fashion without any other result. Now pair it with a reverse Carnot engine as shown by the figure. The net and sole effect of this newly created engine, consisting of the two engines mentioned, is transferring heat from the cooler reservoir to the hotter one, which violates the Clausius statement. Thus a violation of the Kelvin statement implies a violation of the Clausius statement, i.e., the Clausius statement implies the Kelvin statement. We can prove in a similar manner that the Kelvin statement implies the Clausius statement, and hence the two are equivalent. Planck's proposition. Planck offered the following proposition as derived directly from experience. This is sometimes regarded as his statement of the second law, but he regarded it as a starting point for the derivation of the second law. It is impossible to construct an engine which will work in a complete cycle, and produce no effect except the raising of a weight and cooling of a heat reservoir. Relation between Kelvin's statement and Planck's proposition. It is almost customary in textbooks to speak of the Kelvin-Planck statement of the law, as for example in the text by Terha and Wergeland. One text gives a statement that for all the world looks like Planck's proposition, but attributes it to Kelvin without mention of Planck. One monograph quotes Planck's proposition as the Kelvin-Planck formulation, the text naming Kelvin as its author, though it correctly cites Planck in its references. The reader may compare the two statements quoted just above here. Planck's statement. Planck stated the second law as follows. Every process occurring in nature proceeds in the sense in which the sum of the entropies of all bodies taking part in the process is increased. In the limit, i.e., for reversible processes, the sum of the entropies remains unchanged. Rather like Planck's statement is that of Ulenbeck and Ford for irreversible phenomena. In an irreversible or spontaneous change from one equilibrium state to another, the entropy always increases. Principle of Carathéodory. Constantin Carathéodory formulated thermodynamics on a purely mathematical axiomatic foundation. His statement of the second law is known as the principle of Karathayatory, which may be formulated as follows. In every neighborhood of any state S of an adiabatically enclosed system there are states inaccessible from S. With this formulation, he described the concept of adiabatic accessibility for the first time and provided the foundation for a new subfield of classical thermodynamics, often called geometrical thermodynamics. It follows from Karathayatory's principle that quantity of energy quasi-statically transferred as heat is a holonomic process function. In other words, though it is almost customary in textbooks to say that Karathayatory's principle expresses the second law and to treat it as equivalent to the clauses or to the Kelvin-Planck statements, such is not the case. To get all the content of the second law, Karathayatory's principle needs to be supplemented by Planck's principle, that isochoric work always increases the internal energy of a closed system that was initially in its own internal thermodynamic equilibrium. Planck's principle. In 1926, Max Planck wrote an important paper on the basics of thermodynamics. He indicated the principle: the internal energy of a closed system is increased by an adiabatic process throughout the duration of which the volume of the system remains constant. This formulation does not mention heat and does not mention temperature, nor even entropy, and does not necessarily implicitly rely on those concepts, but it implies the content of the second law. A closely related statement is that frictional pressure never does positive work. Using a now obsolete form of words, Planck himself wrote, "The production of heat by friction is irreversible," not mentioning entropy. This principle of Planck is stated in physical terms. It is very closely related to the Kelvin statement given just above. It is relevant that for a system at constant volume in mole numbers, the entropy is a monotonic function of the internal energy. Nevertheless, this principle of Planck is not actually Planck's preferred statement of the second law, which is quoted above, in a previous subsection of the present section of this present article, and relies on the concept of entropy. A statement that in a sense is complementary to Planck's principle is made by Borgnacker and Sontag. They do not offer it as a full statement of the second law. There is only one way in which the entropy of a closed system can be decreased, and that is to transfer heat from the system. Differing from Planck's just foregoing principle, this one is explicitly in terms of entropy change. Of course, removal of matter from a system can also decrease its entropy. Statement for a system that has a known expression of its internal energy as a function of its extensive state variables. The second law has been shown to be equivalent to the internal energy U being a weakly convex function, when written as a function of extensive properties.